We've already discussed the basic model for a DC motor. In this model, I have a resistor, an inductor, and a back EMF voltage supply in series. And that's effectively describing my DC motor that I have. And I can drive that DC motor. I can make it spin around and apply some load torque to some kind of load if I apply a supply voltage to that DC motor. So that will provide a current through that coil, which both generates a torque and also a back EMF. And so by going through Kirchhoff's voltage law previously, we came up with the following equation to describe the DC motor. Vs is T, which is my torque, over Kt, which is my torque constant, times R, which is the resistance in my coil, plus Ke, which is my speed constant, times my speed. So I can do some algebra and rewrite this in two ways that will be useful for me to look at. And the first, I'll look at everything in terms of the speed. So in this case, my speed is equal to Vs over Ke minus R times my torque divided by Ke Kt. I can alternatively phrase this in terms of my torque. So my torque is equal to my torque constant times my supply voltage divided by the resistance in the motor minus those two constants, speed constant times torque constant, divided by the resistance in the motor times my speed. So the two variables that you can see are kind of interestingly dependent on each other are going to be this speed and this torque. And so really what we want to highlight here is the relationship between these two variables. I'm going to start by looking at this first iteration of the equation. And a really good way to look at this would be to set my torque equal to 0 and look at effectively the maximum speed, right? If torque is anything greater than 0, right, my speed is going to be something other than that max speed. So in this case, if I set torque equal to 0, I'm going to get omega, and we're going to call that the no load speed, or often NL for short, is going to be Vs over Ke. So that's the maximum speed that I'm going to get out of the motor when there's no torque that needs to be applied. So that's my maximum speed. So if I'm plotting this, maybe this goes somewhere here on this y-axis. So here I'm plotting speed versus torque. And so here I'm going to put my no load speed, right? So that's when torque is equal to 0, that's going to be the maximum speed that I get. So similarly, if I look at the torque, I'm going to get my maximum torque when omega is equal to 0. So in this case, if I set omega equal to 0, I'm going to get what we call the stall torque, and that is going to be Kt times my supply voltage divided by the resistance in my motor. And that stall torque is the maximum possible torque that I can get out of this motor. So this is if the motor is trying to turn something and it's stalled, which is not moving, right? So omega equals 0. So this one would go over here somewhere. I'd have my T stall. So what I'll find is that I have a nice linear relationship between that no load speed and that T stall. And the slope of this curve is going to be minus R over Kt times Ke. So if I have a higher resistance, but my Kt and my Ke stay the same for some reason, right, I'll have a steeper slope here. I can also look at the effect of the supply voltage on this curve. So this was at some given Vs, but let's say I apply 2 times that voltage, and let's see what happens. Right, so my no load speed is directly proportional to that supply voltage, and the same thing with my stall torque, also directly proportional to that supply voltage. So if I have 2 times the supply voltage, I'll get a different no load speed, so that's at 2 Vs, and I'll get a different stall torque, that's also at 2 Vs. And so I get a curve in this case that looks like this. So this one is when I have 2 times that original supply voltage applied to my motor. So if I apply more voltage, I can get both more torque and more speed. And what this line is telling me is that I can operate anywhere along this line. So I could operate at a torque and speed corresponding to this point right here, for example. I could change the voltage to get some point in between these lines, right? I could use, say, 1.5 times that original supply voltage and get somewhere in between here. So I have various knobs that I can turn. I can change the supply voltage. I can change the load on my system to control the speed, for example. I can change the speed, and that will ultimately give me a different load that I can apply. So there are a lot of different things to think about in terms of understanding this torque-speed trade-off. But there is a clear trade-off, right? If I have a higher torque applied to my motor, if I'm trying to drive a bigger load, then I'm not going to be able to drive it as fast. And similarly, if I'm trying to drive something really fast, I'm not going to be able to support as high of a load on my motor. Let's go through a quick example where we look at that trade-off. In this case, you have a random motor sitting around where it has some specifications that you've, say, looked up on a data sheet or measured independently. And you have a no-load speed of 9,550 RPM. You have a coil resistance of 2.32 ohms, and you can apply a supply voltage up to 24 volts. And so the question is, can you provide 225 millinewton meter of torque to drive a fan at 2,000 RPM? So if I break down this particular example, I'm trying to reach this particular speed and this particular torque. And I want to see if these motor parameters allow me to do that. Okay, so if I plot this on the torque speed plot that I've been looking at earlier, I'm trying to reach this point where I'm operating at 2,000 RPM at 225 millinewton meters. So I'm going to try to see if I can find a voltage where that actually is the case and I can actually handle that voltage. So some other numbers that I can put in here, I know my no load speed is close to is 9.55 kilo RPM, so that's somewhere up here, 9550 RPM. I haven't given you a stall torque here, but it's something that we could actually calculate. So the first thing I'm going to do is try to figure out some of my motor constants. And I have been given my no load speed and my supply voltage, and what you may remember is that no load speed is equal to Vs over Ke. So using that, I can find that Ke is equal to Vs over my no load speed. In this case, it's 24 volts divided by 9.55 kilo RPM, which gives me approximately 2.5 volts per kilo RPM. Using that, I can calculate my torque constant, which remember was 9.55 times 10 to the minus 3 times Ke, when Ke was given in volts per kilo RPM. So this is going to equal 24 millinewton meters per amp, or equivalently 0.024 newton meters per amp. So one approach at this point is to compute the stall torque. So if I'm computing stall torque here, I'm going to have my Kt times my Vs divided by R. And this gives me approximately 248 millinewtons here. So I can plot that stall torque right here on this axis, and obviously all of this is approximate, and draw this line between my no load speed and my stall torque. And in order for this to work, I need this star to kind of fall on this side of the line here, right? So all of these are acceptable things because I could just lower the voltage that I'm applying and still reach that point. But this is pretty close, right? And maybe I haven't drawn these things perfectly to scale, so I'm actually going to come up with an analytical way to look at this other than just the basic graphical way. And this comes from manipulating that basic torque speed equation once again. So my torque I can think of as well as Kt times Ke over R times the no-load speed versus the speed that I want to operate at. And so I can plug in my numbers here, and what I get in the end is that I can, at that speed and at that voltage of 24 volts, I can apply a maximum torque of 196 millinewton meters. So that means that this right here, this point on this line, is that 196 millinewton meters right here. So I cannot get the 225 millinewton meters that I need to apply at the 2000 RPM. So this motor effectively would not be sufficient. If I could apply a little more voltage to this, right, I might be able to bump this up so that I could provide that 225 millinewton meters, but I would have to be able to apply more voltage without melting my motor. So I probably need to get a new motor in order to meet these particular requirements.